Welcome dear students. So in the previous videos we have discussed about the properties of normed space, some examples. So we have established that associated with every norm there exists a metric space. There exists a metric which is defined as the metric is defined as d of xy should be equal to norm of x minus y. Okay. This was the thing which we have established or which we have studied. Now the question is, does the reverse hold? So that is, can you say that every metric is induced by a norm? Here we established that a norm is inducing a metric. This is what we have established. Every norm induces a metric which is defined as norm d of xy is equal to norm of x minus y. Now the natural question is, does the reverse hold, or does every metric is induced by a particular norm? For that, for understanding this question, we need some characteristics, some characteristics of the matrix which is induced by NO. So this is what we have been studying in this lecture. So our question is, does every metric is induced by NO? To get a better hold of that question, we will try to understand, is there any characteristics for the metrics which are the metric spaces which are induced by a particular norm. So the main characteristic is being quoted as a theorem. It is known as translation invariance. Okay. So the result says that if we have a metric D, if D is the metric induced by a norm on a normed space X, then it satisfies one. The first condition is d of x plus a, comma y plus a is equal to d of x comma y for all x comma y belongs to x. That is, if you translate the position of x and y by a distance a, x is replaced as x plus a and y is replaced as y plus a, and then find the metric d, then it should be same as the metric at x comma y. So the changing the position or changing the position by a distance capital A on both the components won't affect the distance which is induced by NO. And the second thing is d of alpha x comma alpha y should be same as modulus of alpha into d of xy, where alpha is the constant or number in the underlying field which is defined on the metric space from which the norm is defined. So this says that if you have a point x comma y, you are multiplying that point by a number alpha, a real number or a complex number alpha, then we take the metric which was induced by the norm, which is defined as d of xy should be equal to norm of x minus y. Okay. Then it should be same as modulus of alpha times d of xy. That is, if you multiply the components by a constant alpha, then the value of the metric is also multiplied by the modulus of that constant. This is what this theorem says. So, we have to establish that these two properties are properties which was been satisfied by a metric which was induced by NO. Okay, so our proof is, it is quite simple. We know that the metric induced by the norm x is of the form d of xy should be equal to norm of x minus y. Okay, so this is the all definition of all the metric which was induced by a norm. So d of x plus a comma y plus a should be equal to norm of x plus a minus y plus a. If you enclose the minus onto the inside of the bracket, this becomes minus a, this becomes plus a, it got cancelled. So the answer becomes norm of x minus y, which is same as d of x comma y. So this result holds. D of x plus a comma y plus a should be equal to d of xy. Now the second property, d of alpha x comma alpha y, by the definition of the norm, which is norm of alpha x minus alpha y. Okay, which can be written as norm of alpha into x minus y. So, if x and y are elements of the space, then x minus y is an element of the space. Using the definition of the norm, norm of alpha into something should be equal to modulus of alpha into that something, norm of something, that is norm of x minus y. This is obtained from the definition of the norm. We know that norm of x minus y is d of xy. So this should be equal to modulus of alpha into d of x. So both the properties has been satisfied. So we have established our proof that every space which metric space which has in which the metric has been induced by a norm should satisfy uh, the translation invariance properties. That means if you multiply the vector by a arbitrary constant, then the metric is being also multiplied by the modulus of that constant. If you change the position of the vector by a small constant a, then the metric does not seem to get affected. So this is what the properties, the elementary properties of a metric which is being induced by a particular norm. Prove that these are the properties of a metric induced by the norm. Now we are going back to our original question. Our original question was, is every metric is induced by a norm? So for every metric, if at all every metric is induced by this norm, it should satisfy these two properties, because every metric which is induced by a norm should satisfy these two properties. So if at all every metric is induced by a particular norm, so every metric should satisfy this property. So in order to prove that the reverse inequality or reverse property does not hold, we should only have to find a particular metric in which these two conditions or either one of the condition does not hold. So which is what we are going to prove. So we are going to find a metric in which the translation invariance does not hold. So which means that that metric cannot be induced from a norm, because every metric induced from a norm should always satisfy the translation invariance properties. So we are going to find a metric which does not satisfy this translation invariance properties. So from that argument, we can clearly say that not every metric can be induced from a norm. So which is what we are going to prove. So our intuition is, or our result is not every metric is induced from a norm. So consider for that, consider a vector space which is not equal to the set sphere space, and define a metric, discrete metric, which we know that d of xy should be equal to 0 if x is equal to y, and it is equal to 1 if x not equal to y. This is what the discrete metric is. Okay. So if we take an element x comma y which are not equal to two elements, then d of xy should be equal to 1. Okay. Choose a number alpha such that modulus of alpha not equal to 1. Okay. So this is what our argument. Modulus of alpha is not equal to 1. Okay. So alpha cannot be 1 or minus 1. This is what we are going to choose. Then alpha of x not equal to alpha of y, because x not equal to y. Then d of alpha x comma alpha y should be equal to 1. Since alpha x not equal to alpha y, by this definition of discrete metric, d of alpha x comma alpha y should be equal to 1. Okay. So from that, we can establish the following simple fact. So d of, for a metric to satisfy the translation invariance property, d of alpha x comma alpha y should be equal to modulus of alpha into d of xy. Okay. So d of alpha x comma alpha y should be equal to 1 by our assumption. Modulus of alpha into d of xy is also 1. So we have already, which implies that modulus of alpha should be equal to 1, which is not true, since we have already chosen that alpha to be a real number or a complex number which satisfies modulus of alpha not equal to 1. So this is not true, which means that d of alpha x comma alpha y should not be equal to what? D of alpha x comma alpha y is not equal to modulus of alpha into d of xy in the case of discrete metric. So we have obtained a metric or a discrete metric in which this condition, translation invariance, does not hold. So the discrete metric is not a metric induced from a norm. So this is what we have established. The discrete metric is not induced from a norm. So in general, not every metric can be induced from a norm. So this is what the result is. We can further give one more example. The example is the sequence space. The sequence space is a collection of all sequence in which we have defined a metric which we have already studied. D of xy is equal to summation j is equal to 1 to infinity 1 by 2 raised to j into modulus of theta j minus theta j divided by 1 plus modulus of theta j minus theta j. In this metric also, d of alpha x comma alpha y need not be equal to modulus of alpha into d of xy, which you can easily prove. So this is also an example of a metric in the sequence space which cannot be induced from a particular norm. So not every metric can be induced from a norm in general.